Okay, so I think this is coming up on the last lecture in the electronic spectroscopy section. So we started out learning about the atomic orbitals, where we had reviewed the quantum numbers and the 1s, 2s, and all of those kinds of things. Then we got into atomic spectroscopy, where we looked at the Grotrian diagram, which was the energy level diagram. And that was tied to spectroscopy because a difference in energy levels gives us those spectral lines. And we also noticed that, like the mercury spectrum and the tube lights, is a line spectrum. So the atomic gaseous atoms have very narrow spectral lines. Then we broadened things out to molecules. We looked at potential energy surfaces and showed that we have a lot of vibrational levels inside those electronic potential energy surfaces. Even if it's a gas phase, we even have the rotational levels. And so we just have really a continuum of energy levels inside the electronic potential energy surface. That leads to a couple of things. One, it leads to molecules having a continuous spectrum. Now, if you have a high resolution spectrometer, you can see the line spectra of molecules, but most of the time molecules, because there's so many vibrational levels, and if it's a gas phase, you have so many rotational levels. If it's a liquid, you don't have full rotation, but you have partial rotation. This is a word for you. I'm not testing you on it, but it's a new vocabulary word. It's called a libration, L-I-bration. So instead of vibration, it starts with an L. A libration is a partial rotation of a molecule. So if you have a molecule in a liquid, some of those motions can be quantized, and you, again, it further blurs out the spectrum. So in the UV vis, we don't have a lot of molecular information because none of the peaks are resolved. So we just have this big blob. So if you remember way back one of the first lectures when we first introduced the failures of classical physics, we talked about the black body radiator. And then we modeled that with the particle in a 1D box. And we saw that there were like 15 or 20 or even 100 transitions under that big blob in the visible region. Do you remember that graph? It had a bunch of little stick spectra and a bunch of little Gaussians on it, and those added up to this overall blob of a peak. That's what we have in the electronic spectroscopy. Okay. But if we put that substance and we do the pachinko game, we excite it and it starts to emit. If we put that emission in between two mirrors, we can get a resonance and we can get a laser. So we've talked about absorption and emission, and most of this time we've been talking about spontaneous emission. So a molecule is in the excited state or an atom, and it just decides from whatever's driving nature to emit that photon. We don't know why it jumps down or when it jumps down. We can look at it statistically, but we can't tell what makes a single atom emit light. If we hit that atom with a photon that matches the energy difference, we can cause stimulated emission. And so we can force it to drop down when we want it to. And if that's between a resonant cavity, this light can bounce back and forth and cause the stimulated emission of a bunch of other atoms. And that's what a laser is. So a laser is light amplification by the stimulated emission of radiation. So even though you might have a molecule that has a really broad spectrum, if you put it in a cavity that wants to highlight a particular wavelength, then you can get amplification of just that wavelength, and you can get a really narrow spectral line. So let's look at lasers today. So this is the helium neon laser. It's very similar to this little diode laser that I have here. Although now we're not using helium neon in these lasers anymore, but we know that atomic spectra give off very, very narrow lines. And so one of the first lasers was this helium neon laser. And you can see that up here. Look how narrow that emission peak is. And even down here in the solar spectrum, you know, these peaks here are pretty narrow, but this helium neon line is even more narrow. It's a little gaseous discharge of helium and neon inside a resonant cavity. So we're talking about the difference between a line spectrum and a continuum spectrum. A continuum has all of the wavelengths of light in it. And so we can make lasers of all different colors. We just change the dimensions of that resonant cavity, and we change the substance that's lasing. So we can fine-tune the substance to have an emission, say in the blue or the green or the red, and then we can put it in a resonant cavity and fine-tune the frequency of that laser. So there's lots of things about lasers, even joking in Austin Powers. I don't know if you saw that. Okay. Yes. So they have multicolored lasers that have substances in them that emit at a bunch of different wavelengths. And so what they'll do is they'll just tune the cavity to pick a different wavelength. So if you go to a laser light show and you see that it'll have a trace that's green and blue and red, and they'll fine tune the colors on the wall. They used to do that with multiple lasers that had the different colors. Then they discovered a titanium sapphire laser. So a titanium sapphire laser, the titanium has a bunch of J values in its term symbols and a bunch of different wavelengths that it can emit at. So they excite the titanium atom inside that solid matrix with a flash lamp or something. We'll see some structures of the laser cavity, and then the mirrors will pick a particular difference between the energy levels. Like it might be these two levels. And then if they want a different color, they might pick those two levels. So they can fine tune and pick the different levels that they want to stimulate, because it's stimulated emission. So once one photon comes out of that atom, then it bounces between the mirrors and it selects the other resonant wavelength and it amplifies that wavelength. So all the other modes are still there for titanium, but they're not resonant with the cavity. So when they get emitted, they don't cause amplification because they're not resonating with the cavity. It's kind of like the fretboard on a guitar. So the strings have a range, so that would be your substance, like your titanium. And then you can change the length of the cavity and change the sound. So we're doing the same thing with light. We're changing the length of the cavity, or maybe we have a grading in there where we can select a particular wavelength that is amplified. And that's like moving the fingers along a fretboard and picking a different frequency. So we have, again, we've gone from the potential energy surface of a diatomic to a complicated molecule. We have this Jablonski diagram. And so there's lots of vibrational levels, but now we'll just draw the energy levels with these lower states. So we're going to get rid of the vibrational lines and just show this lower line, but realize on top of all of these lines that we draw in the next few energy level diagrams, we have the vibrational levels on there. Okay. And so here's the neodymium YAG laser, a very common laser. This is the laser that you used for the Raman experiment. So upstairs, the little blue box with the red button on the front, that was a pretty bright laser. And it was, the YAG part is yttrium aluminum garnet. So this is let's start with the G, garnet. It's named after a gemstone because it's the particular crystal structure of the garnet crystal structure. And it's made out of aluminum. Aluminum oxide is in the garnet. So this is aluminum. And then it's doped with yttrium, okay, which is right there at element number 39. And then it's further doped with neodymium. And neodymium is the actual lasing atom. This little gnat's flying on my face. And these are the energy levels for neodymium right here. So we need a way to excite this neodymium atom inside this crystal structure. Now, I told you about the emission lines for a gaseous atom are narrow because the environment of that gaseous atom is uniform. So a mercury atom here or there all have the same environment around them. They're in the gas phase. Does that make sense? So their energy levels haven't been perturbed at all. It's the perturbing of those energy levels that smears out your spectral lines. So in a liquid, it's chaotic and everything's next to a different set of nearest neighbors. So a liquid spectrum is all broad and ugly, but a gas phase spectrum is very nice. Well, also a crystal phase. If you put an atom in a crystal, we're back to kind of like a gas phase, and that the environment's the same around every neodymium atom. And so we have very well-defined energy levels, and that gives us very narrow spectral lines. And so a crystal structure is very good. And so this would be the energy level diagram for the neodymium. And so we start pumping it with light, and we get some neodymium atoms that are excited. And they go up to that metastable state. All that means is that's a state with a very short lifetime. So it falls down pretty quickly. If we're hitting it with a bunch of photons of light, we excite a lot of those neodymium atoms. And sometimes they don't get all the way up. Like that one bounced back down. Then another one goes, and it ends up in that metastable state. And then the first one drops down just by nature. So that would be spontaneous emission, and it drops down by itself. And then more of them keep going up. Okay. And so what we're doing here is we're doing pumping. So we're pumping those neodymium atoms into an excited state. And this is very important right here. You see this population inversion. That's the key to a laser. Because what happens is when this drops down to here, to this level, it emits a photon of light. Okay, and that causes this one to drop down at the same frequency and in phase. So this one spits out a photon of light. And then this one drops down. They cause just the interaction with those other atoms. If that photon goes past that other atom, it can stimulate an emission event, and it comes out in phase. So you see, this is light amplification. The first one comes out, then it causes the second and the third and the fourth to come out. And in fact, if we get a good pumping mechanism, we can get billions of atoms in the excited state, and one pass through the resonant cavity can multiply that one photon by 1 billion. So we can get 1 billion photons, and then it passes back through, and those 1 billion photons can stimulate. If you have enough efficient pumping, each one can stimulate another 1 billion photons. So now you have 1 billion billion. You have 10 to the 18 photons. And that's actually something you can do something with. Okay. When you start getting up into the 10 to the 18, 10 to the 20, you're in the mole range, right? 10 to the 23rd. And that's the kinds of ranges that we deal with. We can weigh out a mole of substance. We can detect a mole of photons. We start getting into the 10 to the 20s. Now it's very obvious what's going on. We see light and so on. So this is like a mole of photons hitting right there and easily detected by your eye. Okay. So the population inversion is really important. If you take the Boltzmann distribution between these levels, like this is Boltzmann. Right? You could calculate, if you have the energy difference and the temperature, you guys are really good. You could calculate the probability of being in the excited state at that temperature. Okay? And it's not very high. So we're hitting it with visible light or maybe even UV light and pumping everything up into the upper state. And so this is absolutely not Boltzmann down here. Not Boltzmann. We have a population inversion. We have more molecules in the excited state than the ground state. That's important because the stimulated emission is the same as absorption. It's the same mechanism. So if this one drops down and spits out a photon, it may not trigger this one to drop down. It may trigger this one to go up. And then there's no more photons. So one photon went from this neodymium atom over here to this one, and it absorbed it. And we've just changed seats. We had one in the excited state. Now this one's in the excited state. So if you have a 50-50 population, that's what happens. Okay, they just change chairs. One's excited, the other one's ground state, spits out a photon, stimulates absorption, and you don't see any difference. In fact, that's what's happening with saturation in a spectral absorption experiment. When you hit it with so much light that it can't absorb anymore. If we have more in the upper state, then there's a net release of energy because we have more in the excited state. So this is how we pump the heck out of these laser tubes. This is a flash lamp pumped laser. And so it's a really clever design. So this is an ellipse here. And so what that is, an ellipse has two focal points. And so you've got the flash lamp here, which is like a lightning in a jar. You have a huge voltage, you shoot it through this lamp, and it's the lightning flashes, and all of that light in that ellipse goes from one focal point up to the other focal point, and the other focal point has the laser rod in it. And so we're just blasting that neodymium, those neodymium atoms with visible light and exciting them. And then you have the resonant cavity set up between these mirrors, the front mirror and the rear mirror. The rear mirror is 100%. The front mirror is partial reflector. You know, you can sputter a certain amount of silver or gold on that glass substrate, and if you don't put enough to have 100% reflectance, you have less than 100%, right? And so it can let 20% of the light out or 50% of the light. You want it to be partially reflective so you can set up the resonant cavity, but you want it to leak out. And the leaky light that comes out is what we can then do spectroscopy with. These flash lamps require huge voltages, so this has got a large power supply that takes a lot of power. Okay, but see, you see that first one emit out, then the second one comes down, and that's stimulated emission, so it's amplified the first photon, and then the next one, and then the next one, and so all of that light is coming out amplified, and the wavelength of the light corresponds to this energy difference right here. So that's what makes the neodymium YAG laser so efficient, is that it's not competing against the ground state. Do you see this? This is the ground state down here, and it's super hard to get a population inversion against the ground state, but it's super easy to get a population inversion against a state that's close to the ground state. Like this one is normally empty. So if I pump atoms up here to this metastable state, then they kind of get stuck for a little bit. It's got a long lifetime. And then it's in a huge population inversion against this empty state. And so it's ready to laze, and put it between a resonant cavity and nature takes over. It's fantastic. Okay, so because all that energy is directed in a particular direction, these can be called directed energy devices. For the military, they're called directed energy weapons. And so now they're using lasers to shoot down missiles and to protect our ships, to stop, the pirates that are coming up and trying to take over cargo ships and so on. I don't know that they're using directed energy lasers with those yet, but that would be a great option because it's very easy to target with this. But these are, again, directed energy. All of this little AA's or AAA batteries, there's two of them in here, are just going right into that diode, and it's creating this laser. All of the energy that's going into that diode that's coming out is going in a single direction, so it's really bright. If I were to take out the resonant cavity and just look at that diode with my eye, without the laser, the light would be going in all directions, and it'd be a very dim diode. But if you put all of that light and take it from all those other directions and put it in a single direction, then it can be really bright. Years ago, I had a really talented student. And so we rate these lasers by different classes. And so this laser here, my eyesight's gotten so bad now. Can you read this? Can you tell what class laser this is?
Class 2.
Class 2, okay. So it says, do not stare into the beam, okay? So class 1 is even dimmer than this. This is a class 2. And so, don't stare into it. That'd be bad. But if it hits you in the eye, it's still eye safe, okay? It's mildly irritating, and that was. Okay, but you don't want to do this. Again, it's directed energy, and so it'd be hitting your cornea, your retina, and just overexciting those cells and harming them, okay?
Kind of like a don't stare to the sun.
Yeah, if you look at it, if you're driving on, right at the equinox, driving on Highway 30 at the light at Veterans Memorial, the freaking sun is right there by the red light, and you're like trying to look, what are you going to do? And so I'm surprised there haven't been wrecks there. Maybe there have, just I haven't been in one. So that's 1 milliwatt. Okay, so it's pretty small. 5 milliwatt laser, you don't want to even get it in your eye. Class 3B lasers may damage skin, and class 4, different powers, they definitely will damage skin. Pulsed lasers are really dangerous. So you can take this laser, this is a continuous laser because it's on all the time. If you store up that energy and then pulse it, you can take, over time, you can take, say a second worth of laser energy and put it in 10 nanoseconds. Let's make it easy. Let's make it 1 nanosecond. Then that's 1 billion times more powerful, right? So if you can get something to spit out that light, and so if we go to 10 nanoseconds, it's 100 million times more powerful instead of 1 billion. But still 100 million. And our laser research that we did when I was in graduate school used pulse lasers, and our pulse length was 10 nanoseconds, and it was it was 10 times a second. And so it was running at 10 hertz, the pulses, and it was 10 nanosecond pulses every 10th of a second. So it looked like a solid beam. You could kind of see that it was blinking, but you could certainly hear it. So the power supply was going at 10 hertz. So it was, and I guarantee if you time me that's 10 hertz, because we were in that lab for hours and hours a day, every day for 5 years. And that's what the speed of 10 hertz is, all day long. And the flashing lights. So, but that laser would damage your skin. We had a person walk in front of the infrared beam. He couldn't see it. The neodymium YAG puts out infrared light. And he walked between the two laser tables while we were aligning things. Normally we have a PVC pipe that the beam went through, so you couldn't walk between the two laser tables. We had that pipe down, we were aligning things. And he comes bopping into our lab, and he walks between the tables, and he goes, ow, ow, ow. And he got shot 3 times with the infrared beam, and it looked like a cigarette burn. Yeah, so he pulls his shirt up and it's like, dang, look at this. Like, and we're like, dude, we're aligning the laser. You don't just come walking around. Yeah, so that's, it will damage skin. Absolutely. 100%. Yes?
So the sun's not a laser, but if you use like a magnifying glass, does that count as a laser then?
It doesn't count as a laser because you're not stimulating the emission.
Okay.
Yeah, so that's the thing that you need for a laser. And that's a great question, because you need a population inversion so that stimulated emission can give you a net benefit.
Okay.
Yeah. So if you don't have the population inversion, then those stimulated photons will just cause absorption, and they'll just change chairs. But if you get more in the excited state than the ground state, then you can have a laser, because you put it in a resonant cavity. And then I've often thought it'd be really great if we could make a solar laser. Like if we could have the sun pump the laser rod, and then we would have the resonant cavity come on and off or whatever, and set up a laser. But you need a really bright collector. You could probably do it with a large enough, mirror, parabolic mirror. Yes.
So the metastable state that goes into,
Yes.
the triplet state, or is that just
Oh, a good question. I don't know. I'd have to go look to see what the term symbols are for all of those. But different states have different lifetimes. Okay. And so I'm not exactly sure why that one's labeled metastable. Okay. One of the first lasers, you might have heard of the ruby laser. And a ruby laser is a sapphire crystal, not a garnet crystal. And the species in there is not neodymium, it's chromium. So chromium in a sapphire crystal structure is actually a ruby. So you want to know more about all that, go talk to a geologist. I don't know all of my gems and all of my crystal structures. Maybe in inorganic, you'll get into that. But if you take the sapphire crystal structure, again, it's an aluminum oxide structure, and you dope in some chromium, it turns red. And the more chromium, the more red it is. And that's a ruby. So, and we can make all of these things artificially. So they'll grow these laser crystals in crucibles. They'll melt all of the aluminum and the chromium and the oxygen and make all this goopy paste, and they'll draw out a perfect crystal of ruby, or they'll draw out a perfect crystal of silicon. That's how they grow our silicon wafers. And so they'll grow these crystals very slowly in a radio frequency crucible, and then they'll cut that rod and they'll use it to make a laser. Again, this is a flash lamp, bulky, water-cooled power supply. So that lightning in a bottle will just drive all of those chromium atoms up to these excited states. And here we have the term symbols. So we have a quartet F2 and a quartet F1. They'll de-excite to a doublet E, and then that's if they pump it hard enough, they can get a population inversion. And here for the ruby laser, they're getting a population inversion with the ground state, which I said was tricky, but if you got a high enough pumping efficiency, you can do it. Big bulky laser, also fragile because it has that glass flash lamp, and also bulky because of the power supply to create lightning in a bottle. So then we started with light emitting diodes, looking at making a laser with a light emitting diode. And the diode lasers really took over. They're cheap, they're solid state, there's no moving parts. That's what solid state means. And so the way we can do this high powered laser is if we can turn the resonant cavity on and off. So this is called Q switching. And we have this switch that a lot of times they're liquid crystals, but anyway, it's a way to, so the light's coming along here and it might redirect it. Like, let me just change it from a wave. Let's just say this photon of light is coming here like that. It would turn around and create more stimulated emission, but it hits the Q switch and it's deflected somewhat. And so now it comes down here and exits the cavity. And then when we turn the Q switch off, I think it is. I think the Q switch is off when it's resonant. Anyway, don't quote me. Anyway, we switched the switch. And now the light is not deflected and it comes back the way it came. And it can go back through the laser rod and it can come down here and bounce back. And so then the resonance of the cavity is restored. When you turn the switch off, then you have the resonant cavity. So you can this allows you to pump the laser up, and you have some spontaneous emission occurring, which would cause it to laze, but we throw those photons away. We don't let them bounce back and forth through the material. So we create a cavity that is leaky so that we can pump more atoms into the excited state, and then we shut off the leak and it resonates like crazy and it shoots out. And so that's a way to, again, multiply the amount of light that comes out of our laser by 100 million in a short pulse. So we build it up for, let's see, I'm trying to do the math in my head. 990 million nanoseconds, and then we shut off the leak for 10 nanoseconds, and all of that light comes out. So that's the ratio of pumping to emission. There was a story in our research lab that our advisor put on the wall. It was a news article, and it was a student at a different university who was aligning the laser with the Q switch going, meaning it was full power. And you're not supposed to do that because it's incredibly dangerous, because you have 100 million times the power than you would have if you turn the Q switch, disable the Q switch. And he was aligning optics and it bounced off his thumbnail. And now it burned his thumbnail for sure, and that's bad enough. But he happened to be looking down to see what he was doing, and the laser hit the thumbnail and hit one of his eyes and just burned a big spot on his retina. So he was blinded in one eye in 10 nanoseconds. So that's how dangerous it can be. And so he should not have been aligning the laser at full power. He should have cut the power back and disabled the Q switch, and everything would have been fine. Okay, then we have the laser emitting diodes. So you have all of these different layers, and you can get this emitting region here. And you can take this solid state diode, and then you can just partially silver the front and the back of this. And so if we put a partial silver coating on the front and a full silver coating on the back, then we can have a diode laser. I've got a book from the 70s, I think. It's a laser experimenter at home. It's like a hobby book. And it talks about filing down laser diodes and putting a mirrored surface on the front and building your own little laser out of it. It's the diode that you buy. And so it's pretty neat. I never have done it, but I always wanted to. Okay. So this tiny little diode laser can then be put into a system that amplifies that light even further. So we go from a diode laser that's about this powerful here all the way up to one that can cause fusion. So this is what the National Ignition Facility is about, this fusion laser facility. It's about like 3 football fields in size. And so we've got some videos here that we can show. But before we get to the videos, I just want to talk about some of the forensic uses of it. Yeah. These are, when you're working with the lasers, again, it's very dangerous for your eyes. And so for the neodymium YAG laser, these are the laser goggles that the Ocean Optics folks sell with that laser system that you used in the Raman. I'm trying to find them. Yeah, it says right here. So it's tuned right to 532, an optical density of 7. So that means it only lets through like 10 to the minus 7 photons. So so you'd have to have 10 to the minus 8 photons, or 10 to the 8 photons for me to get 10 photons through these. So it knocks out, a factor of 10 to the minus 7. So you put these on and then you can work with that green laser, but the downside is it completely blocks the green laser. So when working with lasers, you're kind of at a loss, because if you want to align the laser and get it to hit a target and so on, you've got to be able to see the beam. But if it's too bright, your eyes are at risk. So you put on your laser goggles and you look and you can't see the beam anywhere. Okay, so they're too good. So then, so you've got to figure out a way to attenuate the signal, turn it down a little bit. You can put it through a wire mesh, but you don't want to steer the beam. So there's lots of problems. So you take other just neutral density goggles. So this is just like sunglasses that you put on, and it just protects your eyes by dropping all of the photons down. And then you can see. This may not be nearly enough or not dark enough for the laser for eye safeness, but it does something. If you spread the beam out, like to look for a survey area, like for fingerprints or bodily fluids and so on, you want to defocus the beam. And then you don't need laser goggles, but you just do need something that's going to block that laser. So you can buy these cheapo plastic goggles that will block out the blue and green wavelengths. And then your eye is more sensitive to the yellow and the red, because it's no longer squinting to kind of cancel out the blue and the green photons. And so your eye opens up, it's ready to go, and then you can shine that green laser around and you can see very sensitively, you can see where all of the fluorescing compounds are. So this is what we use. Now, I had a pretty talented student a few years back, and he made this. Like, he took a flashlight and took all the guts out, and he took the laser off of an old Blu-ray DVD set. I didn't know those lasers were this powerful. But this laser, he made it himself. We don't know what class it is because it hasn't been evaluated. But it is way more powerful than it should be. Okay, so I'm going to shine it at the board, and you can see how bright it is. This is not an eye-safe laser. I'll shine it over there. Why is it not staying on? The battery may be dead. There it goes. Yeah, and so that's pretty bright. Yeah, so it's kind of old, so it's not. Maybe the battery's bad, but anyway, that's. I was messing around with it. I put on like a couple of these goggles, and it was still like making like a flashlight, spots on my eyes. I was like, okay, I've been looking at this too long. But I focused it down. There's a little lens on the front. You can focus it down, and it was catching paper on fire. So yeah. So anyway, that's not good. I think it just needs to be charged. I'm glad it came on long enough for you guys to see it. So anyway, the bottom line is the laser goggles are great, but they also kind of harm your ability to work. This one's like a multi-wavelength laser goggle. Let's see, it's broadband 190 to 380 and 765. So there's a 765 laser, a red laser that it blocks 100%, almost 100%. So you can put these on. It's kind of a cool color. But again, it's a catch-22. If you're going to work with lasers, you want to get laser goggles, but then they blind you to what you're working on. So that problem hasn't been completely solved, except to just sort of put something, a neutral density filter, in front of the beam so that it's at eye safe levels, and then you can work around with just regular eye protection. Let's look at some of these videos. Well, before that, we'll come back to this. Let's look at some of these. So here's the ruby sapphire laser on the left, the neodymium YAG laser that we talked about on the right. Okay, it's the Quartet F and the Quartet I. So those are the two energy levels that are combined in this one here. And again, the Quartet F and I, those are the capital L's, those are the term symbols. And so you would have to figure out how many unpaired electrons are there in the Quartet F. So that multiplicity, that 4 is the multiplicity, and that's always the number of unpaired electrons plus 1. So it's 3. 3 unpaired electrons in that. And then we're going down to a Quartet I, so also 3 unpaired electrons. And so one of those electrons is just hopping from one level to another, and then the L1 plus L2 plus L3, because there's 3 unpaired electrons, one of those combinations is S, P, D, F, so an L of 3. And then it's going down to an S, P, D, F, G, H, I. So an L of 6. So that's what's happening with those term symbols. Then we have the helium neon laser. So helium, we know the electron configurations here. It starts at a 1s2. One of those electrons hops up to the 2s. It's a singlet here. If it goes at a singlet emission, it's up there higher, 1s1, 2s1 at a singlet s. And then it also, if that spin flips to a triplet, it lowers its energy a little bit. So the triplet s is a little bit lower. And this is kind of a weird thing that we've never talked about. This is collisional energy transfer. We've never talked about this. You've got a helium atom running around with its electrons in different orbitals, and it bumps into a neon atom, and the neon atom says, hey, that's cool, and the helium drops this back down to the ground state, and the neon now is excited. So that's weird. We haven't had any photons of light change place. We just had a collision, and the energy levels match. So the energy level in helium matches an energy level in neon. And so when those electron clouds interact with each other, one relaxes and the other excites. So it's collisions, but what's colliding when atoms collide? It's the electron cloud. So the electron cloud in helium has a resonant energy level, and the electron cloud in neon has a different resonant energy level, but it's the same frequency, and they bump into each other and they exchange excitation. So the helium drops down, the neon is now excited, and then look at the neon. It's got a lot of electrons, right? It's 10 electrons, and it's got a lot of different energy levels. And so now we have a population inversion in the neon, and we put that in a resonant cavity and we get a laser. Sounds overly complicated, but it works. You put a certain mixture of helium and neon into a tube with mirrors on each end, run a little bit of electricity through there, excite those atoms, and this laser light comes out. Okay. So how they discovered that, I do not know. It's great. 1960. I mean, that's incredible. They were bright. Okay. Things have really advanced. These are different tunable lasers. We also have some non-tunable ones. So across the top, we have a lot of the atomic lasers. So I know you can't really read that, so I'll just sort of point some of them out to you. So here in the visible region, that's 632 nanometer light. So these right here are the helium neon laser. You'll hear people talk about the Heine laser. Okay. We talked about the neodymium YAG. It's over here, this neodymium one. And notice it's in the infrared. That's not really useful if you want to do fluorescence. Okay. And we haven't talked about it in this laser chapter, but if you take that infrared photon, I'm going to draw a really long wave photon, and it goes into this system here. There's certain crystals, potassium deuterium phosphate, I think, KDP. And it doubles the frequency or halves the wavelength. So 1064 comes in. Uh-oh. Okay. My pen's acting up. And 532 comes out. So we've doubled the frequency, we've cut the wavelength in half. And so up here at 532 is the neodymium YAG laser also. Well, we could do that again, and we could get the 355. So if we take this neodymium laser and then we double the frequency, we cut the wavelength in half, we're at 532. That's the one we have in the lab. So we've taken all of these wonderful photons in the infrared, and we've thrown away about a half of them, and we get the 532. And then if we wanted to double that one, we could make it into a UV laser. Still, these are not very useful for molecular spectroscopy. They're great for emission or for fluorescence, but what if we wanted to do absorption spectroscopy? We would need to tune the light source. What do you have in instrumental? You've got a light source and you've got a monochromator. And the monochromator tunes the wavelengths of light that you send through your sample. And we can do that with lasers if we have a molecular system that has a continuum of emission. So down here at the bottom, all of these guys, these are tunable dye lasers. So you have an organic dye with a really broad spectrum. When you look at the broad spectrum here, you put that dye in a resonant cavity, that inside that cavity you have a grating. So you've got a mirror. Let's just draw it down here. Let's say you've got a mirror here. You've got the dye. So we'll take this dye here and we'll stick it in this cuvette. Then we've got a grating. Like my grating? Okay. And then you've got a mirror over here. And so this cavity now is resonant through that grating with a particular wavelength of light. And so even though that dye could emit in this really broad mishmash of a continuum of a spectrum, we're selecting a particular wavelength that's going to be stimulated, emitted. And so then we can tune this dye. We just change that grating, and that bright laser then steers its wavelength of light, and then we can do spectroscopy with it. So a broadly tunable mid-infrared source is highly desired for trace analysis and gas phase analysis. And so we don't really have those. See down here in the mid-infrared, we don't have a lot of options. The options we have are expensive or somewhat bulky and kind of a pain. So there's still advancements to do in infrared spectroscopy using lasers. We'll end up with these really broad, not broad, but strange systems called excimer lasers. When we talked about potential energy surfaces, some of those energy levels were dissociative, right? So this right here, notice this one has a dip in it. So this is really interesting. If we have argon in a glass tube and we run electricity through it, we get excited argon atoms. The excited argon atom can get next to a ground state argon atom and form a dimer. Okay, so this is an excited dimer. They can form like a diatomic molecule with like a bond order of a half. So it's a really weakly bound diatomic. And then we can put that in a laser cavity, and it's by definition going to have a population inversion because the ground state argon atoms have a bond order of 0. They're not bound. So you can never have any ground state argon dimers because argon doesn't form a dimer in the ground state. But if you excite one of those argon atoms, then you can have a dimer. So this is a chemical laser. We put excited molecules together in the gas phase. They make a bond, they emit their light, and then they dissociate. And there's never a ground state to compete with. So we have, by definition, a population inversion. So the military has done a lot of advances with this because this is some really high-powered, super high-powered lasers that can be created on the fly. Literally on the fly, they have them in airplanes. Okay. And so only the excited state is bound, therefore you're guaranteed to have a population inversion. And here's the anti-missile system laser, this one in the middle. And so that's flying on a 747. The body of the plane is filled with the laser. Okay, so it's super high powered. It's got this little optic nose that can direct it. And so in a missile in its launch phase, when it has all of that propellant on it, they can shine a laser light on the side of the missile and burn a hole in it. And then all the gases start escaping out the side of the missile and it explodes. So this is ballistic missile defense. They also put them on this little C-130. And so what's the advantage of a laser? Well, it's way faster than a bullet. Okay. And so when you target something, you don't have to worry about the wind speed or the time it takes for the bullet to get there. You lock onto it. You can hold the energy on your target. The downside is it's slow. It takes a while to heat up things, but as you can see this. Now, you're probably not going to come across the military application of lasers, but you might have laser surgery on your eyes. Right?
So
Yes.
For the naval fighter planes,
Yes.
they use like laser lock. Is that like similar, just not as like the 5,000?
Yeah, so they're not using the laser in that situation to attack. It's for targeting. So you can have an optic on the bomb that feeds its fins. And so since the laser's so bright, even in a room with the lights on, you can see that bright spot. And so even in daytime, this bright targeting laser can target what the bomb should hit. And then the bomb can adjust itself to that. Yeah, so the bomb is looking for the laser wavelength, and it's got a computer on board that only looks for that. So it's not going to be distracted by a campfire or something like that. And then they shine the illuminator on it. The bomb acquires it. Like Maverick, remember, is like he's got the illuminator pod, and the other guy's like, I'm trying to acquire. Once he acquires, then the bomb's got the target. And as long as you hold the laser on the target, the bomb will go and hit that spot. So the precision targeting has really reduced the civilian casualties in a lot of these conflicts because it's specific. It's very, very narrowly focused. I don't really like talking about all that, but it's actually turned out to be a good thing in terms of hitting exactly what you want to hit and not having to like blow up a whole city block if you're trying to hit one thing. What's that?
So we don't have stuff like the Blitz anymore where they just launched everywhere.
Just yeah. I can't say we won't ever do that again, but yeah, this has been one of those things that's, I guess, been a good development. I think also, like we've seen this laser, the Navy one here. Let's see if we have time to see it. Let's move this up.
Well, the end result is what is it? Let's try to
It's not working.
The documentary that we're about to watch explores the hot-button issues of transgenderism.
That's not it. Yeah. And so they do the same thing with the Exoplex laser on your eye to adjust the shape of your cornea. Really hard to watch for the spouse. I watched my wife's surgery. They come and they cut the cornea, make a flap, flip it over, and then they just use the laser to destroy parts of the cornea and reshape the lens. And then they flap the flap over, put a protective contact on it, and say, you're good to go. And it corrected her eyesight in probably 1990, and she didn't wear glasses for maybe 15 years, 20 years. So it's really, really a good surgery, pretty safe. The only thing that the guy said would cause it to go poorly is if she sneezed. But the laser system has a tracking device. They put a couple of dots on the white part of her eye so the computer could lock on to the position of her eye. And I could watch. I mean, I was in the control room. I was like a kid in a candy store. Her eye looked perfectly still, but I was looking through the laser system. And he said, here's the live view. And her eye was twitching and moving around. And he said the laser is tracking her eye and it locks on. And so it's going exactly where it wants to go, even though the eye is moving the whole time. So it's really cool. It said it can move 100 times a second, and your eye can't move that fast unless you sneeze. You close your eye or whatever. So anyway, it's great stuff.